So our discussion around our Ferrari problem here led us to the conclusion that if thrown perfectly straight up without wind resistance, the phone should drop directly back into the Ferrari. And of course, the expensive and fabulous demonstration here did not help that case, but did show that it basically went to the side as this veered off to the other side. And that goes back to something that we had seen in an earlier lab where we are looking at the motion of a particle through the air, that the velocity in one dimension doesn't affect velocity in another dimension. So that we keep x and y completely separate, and we've been doing that through this projectile motion. The last topic on here, which is called relative velocity, extends that as well. So there are two sort of important concepts along with this relative velocity. One is that if you've got a so-called stationary observer, say here, and that person is watching two things moving relative to each other, you see some sort of an addition. So let's say that you've got a vehicle here, we'll make it a pickup, and there's a person in back, and of course this is traveling because this is farm country and that's what's happening. So the whole truck is traveling. Perhaps it's rolling unmanned down the road. I don't know. I can envision this happening. And somebody's out the back, probably throwing pumpkins this time of year out the back. There's a pumpkin.
We could use my truck.
I'm not actually looking for volunteers for this. Let's say that this person is watching all of this happening, probably drinking non-concernedly and saying, I wonder if this is going to result in stitches or coffins. Let's watch. Well, and so the person is watching, it's watching the truck go by at, say, 15 meters per second. And pumpkins are heavy and they're hard to throw, so probably only about 9 meters per second. If the pumpkin thrower can throw the pumpkin at 9 meters per second normally, and throws it in the same direction the truck is moving, what is our observer going to observe for the total velocity of that pumpkin compared to him?
24 meters per second.
You add them, right? Because you've got two velocities, v1 plus v2. You'd have 15 meters per second plus the 9 meters per second. And you would observe 24 meters per second total. What if our pumpkin thrower gets disoriented, which is probably part of the reason they were in the back anyway, and instead throws it backwards at 9 meters per second? Subtract them because they're just opposite. Yeah. So that option would be v1 going this way. Oops, not vi, v1. And v2 going that way. So you'd have 15 meters per second minus the 9 meters per second. And so the observer would measure 6. Okay, that's pretty straightforward. What happens if, upon seeing this bystander, throws straight out? So let's say that they're here. I can equally see this happening, and I'm just going to get rid of that. And let's say our pumpkin chucker says, I'm going to get you good. Throws the ball out here, v2, 9 meters per second, and it throws it straight out. What's going to happen to our pumpkin now?
Trigonometric.
Yeah.
What do you say? Trigonometric.
So you're gonna have the faggot.
It's like trichinosis, but It's for math.
No, I just bang my head on the table now.
Now we have to consider this is more. This would actually be sort of our three-dimensional problem, projectile motion. But we'll simplify it a little bit. We start out with a velocity in one direction, but we add a velocity in another direction. And we have, because they're in opposite directions, we can't use simple arithmetic to add them. We have to use vector arithmetic. So actually, the pumpkin would move like this, and it would also, of course, accelerate down towards the ground, but just looking from above. So this bicycle would actually be safe, at least from that flying pumpkin, because our yokel in the back would probably not take that into consideration. This highlights what we've seen in a lot of the projectile motion, and the last part we're going to talk about today is that if you've got two motions in opposite directions, they are independent of one another. And so this travels a distance in, let's call that the y direction. And that distance is only affected, or it's only the y velocity moves in it. Our x velocity doesn't make any difference at all. A really common math type problem puts this in another perspective of a river. So let's say that you have a river to cross, and the river is 150 meters wide. And you start up here, and you can swim, you're a good swimmer, you can swim at 4.5 meters per second in calm water, but this is a river. So the river is also flowing at 2 meters, I'll call it 2.0 meters per second. Well, your path is going to be like the pumpkin. You're not going to be able to swim straight across by aiming straight across. If you aim straight across, you're going to get the vector addition of this. So, here's my question. With that, how long is it going to take you to swim across the river, to get to the other side?
33.0 seconds.
How do you know?
150 divided by 4.5.
Well, what about the 2? Keep going.
That would just mean you go down farther. Doesn't affect how long it takes you to cross.
Yeah. These are independent. So these two determine how long it takes you to cross. This one helps determine where you're going to end up. So let's take a look at this. So we'll call this x and this y. And let's do these separately. So in the x, Jacob's absolutely right. We've got a velocity here. Velocity in the x is 4.5 meters per second. The change in our displacement in x is 150 meters. We want to know how long is it going to take us? Well, this is a velocity question. So velocity is equal to a change in position over time. We just have to rearrange this to get time. So multiply both sides by time and then divide by the velocity. Be our change in position over our velocity in x. Oh, we have those numbers. 150. Oop. I wrote that backwards. Delta x. Wrote that weird. 150 meters over 4.5 meters per second. And you said it took us how long, Jacob?
33.3 was 80 seconds.
33 seconds. Yes, Hannah.
So, but if you were trying to get like out.
We'll get there too. Let's do it, but one at a time. So we're just aiming straight across. We can do the same thing in y. We know delta y, say, just rearrange this as equal to the velocity in y times time. That's actually part of one of our normal equations. And we just figured out how long we're going to be in the water. 33 seconds. It takes us 33 seconds to go across. Now let's see how far we float downstream. So 2 meters per second times our 33 seconds be 66 meters. So while going 150 meters across, you'd also go 66 meters downstream. Good?
Would it have to be negative 66?
No, because up here I said, I'm only moving in that direction, so I'm calling it positive.
Okay.
You usually get to decide what the positive and negative directions are. Convention says that if we are going up, it's positive, and down negative, but upstream and downstream like this are a little different at least.
Okay.
So Hannah had a good question. What if I want to go straight across?
Trigonometry.
We'd have to go at some angle upstream, right? So let's set that up. Let's consider that.
Wouldn't you do it just as like a simple right triangle and do trig?
Mm-hmm.
If you're going 150 across, and you now have to aim a 66 up on the other end.
Not 66. So let's see how else we can handle it. So as you said, we've got a 2 meter per second going down. We want to go straight across. So here's our new velocity, we'll call it total. We're gonna have to aim up like that. We don't know what angle yet though. So we can't say how long it'll take, but we do know that I can swim at 4.5 meters per second. So we're actually looking for this is going to be our hypotenuse. Our total is actually gonna be whatever we get when we add these two. Like so. How can we find that theta?
Inverse sine.
Inverse sine. We have the opposite and the hypotenuse. We can just use the sine. So we know that the sine of theta is equal to our opposite, 2.0 meters per second, over our hypotenuse, 4.5 meters per second. Or the inverse sine of this is going to give us our angle. Here we have a chorus of measurements. How much? 26.38, so about 26 degrees. Upstream. If we're going 26 degrees upstream, what is our V total? We could do this with Pythagorean theorem, right? Because we know that 4.5 squared is equal to 2.0 squared plus V squared, we'll call it. And so our V total is going to be the square root of 4.5 squared meters per second squared minus 2 squared. So our velocity straight across, how much?
4.0.
So 4 meters per second. Now it becomes just like our last problem. We're going 4 meters per second across 150 meters. That's going to take almost 40 seconds. We're not going we're going straight across, so we don't have to worry about a delta y. So we could figure out delta x is equal to our velocity. Oops, we know the delta x. Our time is equal to our delta x, like divided by v. I'm hurrying because we're almost out. 150 meters over 4.0 meters per second. It'd be 38 seconds. So it would take us a little longer, but then we wouldn't go downstream. So the last problem set now is dealing with similar types of questions. You've got to keep the x and the y separate, but otherwise they're not very hard questions. The trick is realizing that, different directions don't affect one another.